Hello students, I'm Sonali Kelkar from City International School and today we are going to do the rest of the topics of our chapter Human Eyes and the Colorful World, right? We have done with the refraction of light through prism, dispersion of white light into 7 different colors, that is Vibgyor, recombination and the atmospheric refraction, that is we are going to do today. So in today's session we are going to do atmospheric refraction, twinkling of stars, then stars seems higher than they actually are, planets do not twinkles, why planets do not twinkles, then advanced sunrise and delayed sunset, then scattering of sunlight and different phenomena related with the scattering of sunlight. So let's start this session. Now, what do we mean by atmospheric refraction? So before we actually go into atmospheric refraction, let's do some of the facts related with atmospheric refraction. So these are the concepts which will definitely going to explain the different phenomena related to atmospheric refraction. Let's see these concepts. The Earth's atmosphere is not uniformly throughout. We know that the Earth atmosphere is not uniform throughout. What do we mean by uniform? It means the density of the atmosphere is changing, right? And why are we so interested in knowing the density? Because we are doing a phenomena, something called refraction, and refraction definitely depends upon the density. Okay, and we know that our atmosphere is made up of different layers of air and having different densities. Even the air which are present in the atmosphere, they have different densities, isn't it? So let's see the different concepts, the other concepts. So it can be considered to be consisting layers of different densities. So atmosphere has layers of different densities which act as a rarer and the denser medium, right? Then some of the air layers of the atmosphere are cold. Children, here I want to ask you one question. What about the air layer? What about the density of the air layer which is cold? Definitely the density of the air layer which is cold is more, right? And what about the density of the air layer which is hot? Definitely it will be less denser as compared to the air layer made up of the cold gases, right? Now, the colder air layer of the atmosphere behaves like optically denser medium for light rays, whereas the warmer air layer of the atmosphere behaves like optically rarer medium, right? Now, what about the position of the air layer which is denser? As we know that the denser material always settle down, okay, and the rarer or the less denser material always goes up. So in the atmosphere we can see the different layers, right? And the upper layer will be less denser, as we know that it is made up of hot air. So hot air always goes up. So the upper layer of the atmosphere, this is my atmosphere, right? I'm writing the short form of atmosphere. So this is my atmosphere. The upper layer are less denser because they are hotter. Okay, because they are hotter. And the lower layer, right? These are more denser, more denser, more denser because they are cold, because they are cold. So here we came to know that our atmosphere is made up of different layers of gases. Less denser is at the top, the less denser is at the top and more denser is at the bottom. And if this is my earth, then I can make out that the layer of the air which is closer to earth are more denser, and which is away from the earth is less denser. And here if I make a sun over here, then what can I find? When a when a ray of a light is coming from the atmosphere, then definitely first it is a vacuum over here, because in the space there is a vacuum, right? So light travel fast in the vacuum. Once it enters in the atmosphere layer, its velocity changes. And when velocity changes, definitely there will be a refraction. So there will be a continuous refraction taking place in the atmosphere, because the density of the air is changing continuously. So light is moving from the less denser medium, denser, to the high denser medium, right? Besides that, there is one more physical quantity of gas. Gas doesn't remain stable. It keeps moving. And we also know that even the earth is it is rotating around itself, right? So because of the motion of the earth, rotating motion of the earth, because of the revolution of the earth, right, around the sun, because of these two movements, even these air layer are keep moving, right? Even these layers of airs are keep moving. They are not stable, right? So because of these two properties of air, okay, the atmosphere has different densities at different level, and light has to travel from the less denser towards the more denser. And we know that when a light travels from a less denser towards the more denser a medium, it bends towards the normal, right? So these three things you have to keep in mind, right? So let's start. Let's see the other part of this lecture. Here is the atmospheric refraction. Now let's see the definition, right? So the definition says that refraction of light caused by the Earth's atmosphere having the air layers of varying optical densities is called atmospheric refractions. Very simple, right? Now let's see in this animation. I have shown an animation over here. You can see how the light is passing through the different parts of different layers of the atmosphere, and you can see there is a continuous, right, refraction taking place in the atmosphere. You can see these are the pockets of air which is also moving continuously, and because of these movements, right, because of the change in the density of the atmospheric layer, there is a continuous refraction taking place in the atmosphere, right? Now where can you observe these type of phenomena in our day-to-day life? Let's have a look, right? If we look at an object through the hot air, right, over a fire, the object appears to move slightly, right? So this is due to the refraction of light which takes place due to the change in the optical density of air, right? This experiment you can do at your home also. You can keep a vessel filled with water on a burner, right? And then you try to put an object behind that vessel, and you see the object through that upcoming stream, right? You will find that the object is waving, right? So this is due to the refraction of light taking place. And why there is a refraction of light? Because there is a change in the optical density of the air around that burner, around that vessel. So this refraction of light, so there are some very interesting phenomena in the nature which is due to the refraction of light. Let's start with one of the phenomena. Here the star, if you see, the star seems to be higher in the sky, right? So this is the star we are talking about. This is the original star, okay? ORG, original star, right? Here is the apparent star position. Apparent means this is not the original position, okay? So the star we see here, there is a certain kind of displacement took place from the real position of the star to the apparent position of the star, right? Now let's understand this phenomena. As the light ray from a star passes through the different layers of the atmosphere. Okay, what happened then? These layers of the atmosphere have different density. Because of the different density, the light is traveling with different velocity, and because there is a change in the velocity at the different levels of atmosphere, there is a refraction, right? And so due to the refraction, okay, the light bend towards the normal at each layer, as I've discussed in the previous slide. Due to the continuous refraction, the light from the stars appears to come from a point which is actually higher than the star. So let's discuss this. If you see a star over here in this diagram, the light is coming from this, right? It bends. Okay, it bend towards the normal, right? If I draw a normal here, so okay, it is bending towards the normal. Again it is bending towards the normal. Again it is bending towards the normal, and ultimately it is reaching to earth, right? If a person is standing here, right? Okay, so light has bended at every level of the atmosphere, at every layer of atmosphere, right? So what is happening? Your mind, our brain, okay, our brain is looking at the star over here, where the two lights emerging from the stars are getting joined here, right? So in our brain uh, reads that the two rays which are coming from this part of the star, okay, two rays which are coming from this part of the star, right? So two rays, if you extend two rays over back, okay, these two rays they are meeting at one point, and this point is a source of light, and whatever is the source of light, we see that object. Okay, so when a light coming from a reflect or when a light refracted from an object and reaches our eyes, only that time we see the object, right? So here the light is seems to coming from this position of the star, which is the apparent position of the star. So I will explain with the help of laser. So let's see here in this diagram, right? This is the original star. The light is getting refracted at each and every level of the atmosphere. It is reaching to our eyes, right? If I extend two lines from my eyes backward, straight backward, right? Because our minds read that the light is traveling at a straight path, on a straight path, right? If I extend two layers of light backward, they are meeting over here. Okay, at this point where the two reflecting rays are meeting is said to be it's said to be the position of an object, that is star. So for us, the star is little raised, right? So here in this diagram also the same thing is shown, right? This is the original path of the light, but this path is every time there is a refraction and light is bent and it reaches to our eyes, but our brain is going to view the object little upward, because our brain is going to, right, make a line, and where the lines are getting meet, okay, there we are going to see the object. So this is the apparent position of the object, which is not the real and which is little bit raised. Now here is the another phenomena which is related to refraction of atmosphere, right? Atmospheric refraction, right? This is twinkling of star. Now I want you all to look at this picture, right? If you look at this picture very carefully, you will see that at some point the brightness is increased, and at some point it is dim. Okay, if you see all this picture, at one point it is very bright and the other point it is dull. So this bright and dull, these two effects, okay, makes the star twinkle. And how does it happen? Let's read it. Okay, So the star go on becoming the bright and dim again and again due to the continuous change in the intensity of light from coming from the star. So it means sometime the intensity of light which is reaching to your eyes is more. That time the star will look brighter to you, and at the point where the intensity of the light is less, that means the light is not falling towards you, probably it is falling the back of you or in front of you. That time the intensity is less and you will find that the star is dim. So this intensity of the light which is falling on your eyes, making the star brighter and dimmer, and this is causing the twinkling of stars, right? So I have explained this everything. Okay, and now let's do the definition. The starlight reaching our eyes increases or decreases continuously due to the atmospheric pressure. And why there is an increase and decrease of intensity of light? It is due to the atmospheric refraction, and the light appears to twinkle at night. Okay, so why don't the planets twinkle when the light when the star twinkles? Why don't planets twinkle, right? So we to know this phenomena, we have to go through in detail. First, uh, let's see this picture. Okay, we have already explained you. I have already explained you about the apparent position of a star, right? Here, if I okay, um, uh, draw a two rays coming from the star, right? Two rays are coming from the star because of the change in the velocity of light. First, the velocity of the light is more in vacuum, but as soon as when it enters in the atmosphere, due to the density of the atmosphere, okay, the light velocity of the light decreases or increases. There are the different phenomena taking place within the atmosphere, and due to this there is a refraction of light. Okay, now these two lights are refracted. Okay, here also I have taken the two rays, they are refracted, they reached our eyes. Okay, now if I extend these rays backward, straight backward, right, they are meeting at this point. At this point they are meeting, so I can see the star over here, which is not the real position of the star. Now coming to the different path of the light taken, different type of the path taken by the light. If you see that light, the path of the light is quite zigzag, right? And due to this, why there is a zigzag path? Because of the refraction of atmosphere or atmospheric refraction. Now coming to the twinkling of the star, as I have told you in the last video, if you see, if all the lights from the star are falling right on the eyes. Now this is the point where the star appears very bright. Now let me take the pen, right? Now if a light coming from the star, suppose this is the star, okay, and the light is coming from the star. While coming from the star, let's take a few light reflected over here, okay, because there is a change in the environment, and few rays refracted like this, right? And there is only the two or three rays which is exactly falling on the eye. So this time the star will appear dim, right? So the in the first at the first instance, when all the light rays falling on the eyes, definitely the star was looking brighter. But in the second instance, when the light rays are getting refracted before they reach to the eyes, actually, okay, so this at the second time the star will appear dim. So this is a cause of the twinkling of star. There is one more cause of twinkling of the star, but not the sorry, there is one more cause of why the planet doesn't twinkle and star twinkles. So let's know the reason. Since the stars are very distant, they approximate point-size source of light. The continuously changing atmospheric changing atmosphere is able to cause variation in the light coming from point size, okay, a point size star due to the refraction, because of which the stars appears to twinkle. Planets are very close to us as compared to the distance between the stars and Earth. The planet seems as an extended source, right? And they appear as a small disk of light. Each tiny points of this disk can be considered as a point source of light, right? And these different point produces either bright or dimmer effect in such a way that average of the bright and the dimmer effect is zero. Hence, the twinkling effect of the planets are nullified and they do not twinkle. Now, let me explain you this in a better manner. They have told that this is a star, right? This is the star, and let's say this is a planet. I'm making planet little bigger because planet is closer to Earth, so they look quite bigger and brighter and they don't twinkle. If you look at the picture over here, this is a planet which is not twinkling. This is also a planet which is not twinkling, right? Okay, there are stars here in this cluster. You can see the different stars, they are twinkling. Okay, now if I see a star, these stars are very, very, very far away. If this is the Earth, if this is the Earth, okay, if this is the Earth, then the stars, the distance between the star and the Earth is very much, okay. Stars are far away as compared to the planets. Planets are close, okay. Planet are close. So this is one of the reason why planet do not twinkle. Now coming to the next reason, that is the star is a point source. Point source means if you see, if you look at the star here, there is one point from where the light is coming, right? So here is the one point where the light is coming, but the earth has atmosphere around it, right? And due to the refraction of the light, okay, in the atmosphere, so due to the refraction of the light in the atmosphere, these stars twinkle. Okay, now coming to the planet, if I compare a planet as a disk of light, as they have seen, they have told here disk of light means it has a different point source. It is made up of so many point source, and each point source of light is giving out light. Okay, each point source of light is giving out light. But if I consider that there are 50 point sources, right? 50 point sources which is giving light, and let's take bright light. Okay, and there are 50 point sources which is giving dim light. Okay, so ultimately what happened, this the strong light and the dim light, okay, it get average out, and I can see the strong light coming from the planet because there are so many point sources. Okay, even if the sum of the point sources are not producing a strong light, okay, a bright light, then there are the other point sources which will cancel out or which will average out the dim effect of the different point sources, and that is why we see that planets doesn't twinkle whereas stars twinkle. Okay, now coming to the advanced sunrise and delayed sunset. Okay, now before we come to know the advanced sunrise and delayed sunset, let's talk about the horizon, right? Now, what is horizon? Here, the horizon or the skyline is the apparent line that separates Earth from sky, or we can say that it is this line. Horizon is this line where it seems that the sky and the Earth are meeting, right? So this type of phenomena you can see when you are standing near seashore during the sunrise and the sunset, right? So what happened in the horizon? Okay, over here you can see the sun. The real position of the sun is here, which is below the horizon. The real position of the sun is below the horizon, right? When the light is coming from the sun, okay, when it is below the horizon, what happened? Due to the refraction of light taking place in the atmosphere, the light is reaching here to an observer, right? And if I extend this line behind, right, I can see the sun is over here, which is almost a 2 minutes before the real sunrise. I can see the sun over here. So there is a raised in the apparent position, right? Due to this, we can see the advanced sunrise 2 minutes before. Coming to the sunset, right? Here the sun has already set. Right? Still, because the sun has already set, and the lights coming from the sun get refracted and observed by the observer, right? If I extend this line straight behind, I see that sun is over here, which is the apparent position of the sun. It is not the real position of the sun. So what happened? The sun is raised over here, and I can able to see the sun 2 minutes after the real sun set, right? So altogether we can see that the 2 plus 2 4 minutes, right? The sunrise to sunset, so this time period is lengthened for about 4 minutes because of the atmospheric refraction. Children, I have given the explanation. Later on you can pause the video and read the explanation. Children, now let's do the scattering of the light by particles in its path, and which is nothing but called Tyndall effect. Before we do, before we, before we, before I explain you why the sky looks blue in color during the daytime and why it looks yellow or reddish in color during the sunset and sunrise, before that I want to explain you something about scattering of light by particles in its path, right? So let's see this diagram first, right? Okay, here if I'm passing a light through the different glasses, there are three different glasses, and the first you can see it is the solution, right? And you have done last year that when I pass a light ray through the solution, I can't see the path of the light. Wow, why can't see the path of the light? Because there is a very less scattering of light which is taking place, okay, over here, and the particles present in the solution has very small, they are very small, right? Let's say less than the nanometer, right? So particles or solutions are less than the 1 nanometer, okay, the size of the particle of the solution. Because of that, the light scattered is very less and I can't able to see the path of the light when it passing through the solution. But what happened over here, right? If I put, okay, some milk over here, right? If I put some milk over here, now you can see it is nothing but the colloid, right? Okay, now due to the particle, the size of the particle has increased. Let's take the size of the particle a little increased over here, right? And I put milk in this glass and there is increased size in particle. Right now, these particles which are bigger than the particle present in the solution, this is a solution which is a plain water with sugar in it, right? Sugar in it, dissolve completely. This is a solution, but this is a colloid. Here we have milk particles which are greater than the particles present in the solution. What happened when the light allowed to pass through this? Okay, I'll explain here. This light is going to, okay, this is hit this particle, and because of that there is a reflection of the light in different directions, right? Okay, and again this rest of the light is going to the same path, and there are different particles in the same path, right? And there is again scattering of light, or we say reflection of light in different direction. So the throwing of light in the different direction, or the reflection of light in different direction, is called scattering of light. And due to the scattering of light, we can able to see the path of the light here, right? Even in the suspension. In the suspension, the particles are even bigger, right? Even bigger. And this phenomena we can see in the nature. Beautiful phenomena you can see every day in your life. If you allow a light to pass through a small window in a dark room, right, you can see the light rays, you can see the path, okay, you can see the path of light. Why this happens? Because there are suspended air particles here, dust particles here, right? Okay, there's gases, different gases and dust particles over here, which which scattered the light, and due to the scattering of light, very important, scattering is the phenomena which is taking place. So due to the scattering of light, we can able to see the path of light. Very important point, right? And this can be seen over here, which is nothing but the Tyndall effect. This can be seen over here in a canopy when light passes through this canopy, right? What happened? There are water molecules, water droplets, right? H2O water droplets, mist. In the mist, there are water droplets, right? They are bigger enough to scatter the light, and we can able to see the path of light. So to know why the sky looks blue or why it looks red during the sunset and sunrise, the scattering of the light is very important, right children? And you know that you can see here the scattering of the light depends upon the size of the particles. The size of the particles in the solution was very less, so we cannot see the scattering of light. Definitely, there is a scattering of light, but our eyes cannot catch it, right? When we increase the size of the particle, right, we can see the scattering of light, and due to that, we can see the path of light. Now, let's do the natural phenomena related to the scattering of light. Okay, here we can see the sunlight coming through the atmosphere, and we know that in our atmosphere there is oxygen, right, nitrogen, right, and there are argon, and there are dust particles, right? I'm writing the short form, PART, right, and water vapors, right, H2O vapors, right, and they are present in the atmospheric layer. Now can you tell me which will be on the top layer of the atmosphere? Of course, the lighter gases, oxygen, nitrogen, argon, right? Dust particles and water vapors, and the particles due to the pollution. There are so many particles due to the pollution. There can be sulfur, there can be chlorine, there can be hydrogen, right? Different particles in the atmosphere due to the pollution, right? So they are near to our atmosphere, right? And the particles, we have already done the size of the particles is very important for the scattering of light. How? Let's see. Now we also know that our white light, the light which is coming from the sun, it is made up of 7 different colors. That is Vibgyor, right? Vib, G-Y-O-R, Vibgyor. Okay, violet, indigo, blue, green, yellow, orange, red, right? So let's see why this sky looks blue. Scattering of the light means to throw light in a various directions, various random direction. We all know that, right? We have done this. The color of the scattered light depends upon the size of the colloidal particles, right? We have seen that if the colloidal particles are small, it is going to scatter a light rays with a small wavelength. right? Okay, now let's do the wavelength. As we know that VIB GYOR. Okay, so let's revise this. Violet has the least wavelength, least L least wavelength, right? Least wavelength. And red has highest wavelength. Clear? Okay. Now this wavelength, the smaller the wavelength, more is a scattering. More is scattering. Okay. So scattering is highest here. Okay. So more is the scattering. If smaller is the wavelength, scattering will be more. So if you go like this, okay, the scattering is more over here and scattering is least here. Okay, scattering is least here. That means the red light is going to scatter least. A red light which have a high wavelength is going to scatter least. A violet light which have a least wavelength is going to scatter more. Okay, children, so this is very important point, right? And the particles which are present in the air atmosphere, that is oxygen, is going to scatter, and when light coming towards the earth is going to scatter the blue in violet indigo blue light most, right? And when by the time this light reaches to the earth atmosphere, the dust particles in the water vapor are big enough to scatter the light, and when they scattered completely, the bigger the particle, uh, they are going to scatter the light having more wavelength, and at the end they scattered so much that ultimately the light turns into white in color. Okay, so the sky till the time the light is coming in the atmosphere at this level, blue light of the Vibgyor had scattered almost, right? And due to this, we can able to see the sky blue. Why can't we see the sky violet and indigo when violet and indigo even scattered? Because there are two reasons. Because our light is more sensitive to blue color, so we are able to see the blue color. Second, the spectrum, okay, the spectrum of white light, in the spectrum of white light, blue and the red color is prominent. Blue and the red color is prominent in the spectrum of sunlight. So either you will say blue or red. Okay, and when light get completely scattered by the bigger particle, that means that light will be white in color. Children, these are the three very important concepts, right? The small particle is going to scatter the light which have small wavelength. Now in this spectrum, we know that violet, indigo, blue have small wavelengths, right? So they get scattered more, right? And the rest of the rest of the color of the light is going to reach the earth. But when they come near to the earth, there are bigger particles which scattered almost every light, and due to that we see the white light, right? Now, okay, this is what is given here. Note that the blue light present in the sunlight is scattered 10 times more than the red light. Then, scattering of the light gives rise to many spectacular phenomena. Tyndall effect we did in our last slide, and red hue of sunrise and sunset, as I've already told you, and the colors we see in the sky are due to the scattering of light. You can see the beautiful colors in the sky, and this is due to the scattering of light. Now coming to the discovery of Tyndall effect. See, John Tyndall was a scientist who did this. What he did, he passed the white light consisting of 7 colors. Okay, he passed through a clear liquid having small suspended particles. And what he saw? Then a blue color of the white light having the shorter wavelength is scattered much more than the red color having a longer wavelength, right? And this is the reason why the sky is blue in color. The color of the scattered light depends upon the size of the scattering particles. I have already discussed this. Let's read it fast. Dust particles and the water droplets suspended in the atmosphere are much larger than the wavelength range of the visible light. Bigger the wavelength, less is the scattering. Okay, we know that the red light has the highest wavelength. This wavelength is the highest, and due to this, because of the high wavelength, red light has less scattering or least scattering. It scattered least, and this is the reason we use a red light as a brake light in our vehicles, right? And even in the signals, the red light is there so that it can be seen from the distance. Okay, this helps to avoid accidents when there is a lot of mist, or when there is a lot of fog during the winter season, right? Smaller the wavelength, okay, more is the scattering. I have made this color blue because it shows, this will tell you that the blue light, or the blue color of light in the VIBGYOR, has small wavelength and more is the scattering. Air molecules, now which molecules are going to scatter this? Nitrogen and oxygen, which are present in the air in the topmost layer of the atmosphere, okay, they are going to scatter this wavelength, right? And that is why the sky is blue in color, and by the time the light reaches to your eyes, it has completely scattered and it is white in color. Why the sky is blue, we have already discussed. Let me just show you with the help of the diagram over here. Okay, as you can see, the different colors, the Vibgyor, different colors of the sunlight, right? The prominent color are red and blue. I have told you, right? When it is passing through this atmosphere here, you can see the blue color has scattered. See, the blue color have scattered by the particles, which are nothing but your oxygen and nitrogen and argon, right? All these light gases, they are present here on the uppermost part of the atmosphere, and they have totally scattered the blue light, right? And because of this reason, the sky is blue in color, right? Sky appears blue because the molecules in the air scattered blue part of the sunlight much more than they scattered red light, right? So here is this is a little bit spelling mistake. Please note that only a light of the blue light present in the white sunlight is scattered by the atmosphere, which makes the sky appear blue. Most of the blue light, this is very important, right? Most of the blue light remains behind the unscattered, due to which the composition of the sunlight remains almost unaltered. Okay, because of this, the direct sunlight coming from the blue sky still appears to be white. The sunlight appears white because most of the composition of the sunlight is an unaltered, right? And that is why it is still appears white in color. Here comes beautiful sunset, right? Why does sun appears reddish at sunrise and sunset? Have you noticed the sun during the sunrise and sunset, children? It appears red. What about the afternoon? Okay, the sun, look at the sun in afternoon. It appears white, right? Why? Let us see. Now, during afternoon, the sun is directly above us. Light rays from the sun takes lesser time to reach us. Hence, there is a less scattering of the blue light, so the sun appears to be white. We have discussed just now that most of the little bit part of the blue light is scattered, right? Because the lesser is the distance, so it is coming across the less number of particles, right? So little bit part of the blue light is scattered, whereas the maximum part of the light, that is the different colors of the light other than the blue, they are still there in the white light, which makes the sun, okay, which makes the sun white in color, which makes the sun looks white in color. The sun appears white. Okay, now let me explain you with the help of a Vibgyor, right? It's like Vibgyor. Okay, now when the light from the sun is coming through the atmosphere, what is happening? The distance is less, right? Due to the less distance, this violet and blue will scatter somewhere over here. Like, let's take the eyes are here, right? So violet and blue will scatter somewhat over here, right? The lights are still coming and the composition are still almost unaltered, right? Okay, and this whole band will reach to the eyes as it is without the scattering of red light. It's only the blue or this violet, indigo, blue light, these three lights which will get scattered, but they are scattering very less, in a very less amount. So the effect is not that much, and still the sun is looking white in color because of the very less, okay, scattering of the blue light. Okay, and the rest of the composition of Vibgyor is same. But what happened when the sun is over here, okay, on the two ends of the horizon, right? So if you see over here, the distance has increased. Okay, this distance from the sun, okay, towards the observer, this has increased, right? So what happened when the light is coming here, when the light is passing through here, the, okay, let me write V I B G Y O R. Okay, so as the light is coming, okay, the violet is getting scattered, the indigo is getting scattered, blue is getting scattered completely, yellow getting scattered completely, okay, orange also completely scattered. Okay, the red light is the one which is not that much scattered, and this red color can be seen by the observer, and because of this the sun appears red in color, or red and sometimes a yellowish red or crimson red in color. The same thing is happening over here. Till the time the light reaches to the observer, violet, indigo, okay, blue completely got scattered, right? Okay, orange, red, there is a very less amount of green and yellow color. Okay, the orange, red color is very prominent in the band of white light. So all these light, the red is not getting scattered that much. Okay, it is still there in the band, and that is why our eyes can able to see the red color, that because the rest of the colors of the light have completely scattered. Okay, so they have completely scattered, they have become white, and the red is very prominent, and we can able to see the sun which is red in color. So during morning and evening, sun is at horizon, light rays from the sun takes more time to reach us, hence there is more scattering of the blue color of light, which is of the shorter wavelength. Hence we are able to see the red color sun because there is a less scattering of red color. So this is today's topic, children. Please practice today's topic, and thank you so much.